Good afternoon, everyone, and welcome back to the third portion of our week of Monte Carlo lectures here at the MTV Summer School. I'm Dr. Sean Clark, Associate Director of the MTV, and it's my pleasure to introduce today's guest speaker. It's Professor Chris Perfetti from the University of New Mexico. He is an assistant professor there, and prior to his appointment, he was a staff scientist at Oak Ridge National Lab. His research interests include sensitivity and uncertainty analysis and Monte Carlo methods for improved reactor physics. So Chris, the floor is yours.
All right, thank you very much, Sean. I will share the screen and jump right into the presentation. All right, that should be full screen. Let me know if it isn't. All right, cool. Hello, everyone. I hope you all have been enjoying the MTV Summer School so far. I found out just before this talk that I'm apparently the last lecture before I believe there's a week break in the summer school. So I hope I'm not the last guy before lunch, but I promise that I'll make this seminar pretty painless and hopefully pretty fun. I actually have some fun Monte Carlo examples inside of it too. So, oops, and I have some bonks too. Okay, so the other focus of the seminar, which I've heard that a lot of people have had questions about, is statistical convergence of Monte Carlo methods. So I'll spend a lot of time talking about that in the second half of this presentation. So first half is kind of introduction and some fun examples. Second half is the convergence piece. So getting into the introduction, as you guys have probably learned over this past week, Monte Carlo is a statistical method for predicting the behavior of particles such as neutrons, protons, electrons, whatever kind of particle you have. The basic idea is that the Boltzmann transport equation is complicated and solving it requires discretizing or averaging in terms of space, energy, direction, all sorts of different variables, which leads to lots of inaccuracies, potentially large memory footprints and all sorts of messy stuff. However, we have a very good understanding of the physics for how like one scattering reaction behaves, or one fission reaction, one absorption reaction. So it's actually quite simple to predict the behavior of one particle, one neutron, for example, at a time. And if we simulate a couple of billion of particles, then we can get a good understanding for the average behavior of particles, for the average fission distribution, that kind of thing in our system. And we use random numbers in the Monte Carlo process to randomly sample things such as how far the particle travels before having a collision, what kind of collision, is it an absorption or a scatter, that kind of stuff. I believe Sean talked about how to sample from these distributions in, I believe, lecture 1 of this week on Tuesdays. So if that is still a foreign concept, go look at lecture 1 from this week and it'll be a good review. So there are some other fun examples of the Monte Carlo method. It was not just first used in radiation transport codes. It's been used all over places for hundreds of years. So this typical example that everyone always gives is the Buffon's needle problem, right? If you have a circle with radius 1 inside of a box with width 1, this is just a quarter of the circle. The ratio of the area of these things is a way of calculating pi. So what you can do is you can use Monte Carlo to randomly sample points within that box and see, okay, is the point inside of the circle or is it outside of it? The ratio of that number of points is the ratio of the area of the two, which allows you to calculate pi. So it's a historical method for calculating pi. It was originally done with a needle and 2 parallel lines. It works that way, and the inventor of it was actually able to compute pi to a couple of digits successfully. It's actually a fairly slow way of computing pi compared to other algorithms, but we'll talk about convergence of Monte Carlo methods and accelerating them and that kind of thing a little bit later. A little bit more of a modern example of Monte Carlo methods is something that I did for fun one night when my internet was out. My internet was out and I went over to a friend's apartment, and these friends, we were all nerdy, we were all gamers. They had a chart of the Pokemon types hanging up on their wall. I guess it's better than a painting or decoration. It's best to have a chart of Pokemon types. It's modern art or something. So for those who don't know, Pokemon is kind of like rock, paper, scissors. So like Pokemon are different. They're like little animals that have different elemental affinities. So there are fire Pokemon, electric Pokemon, water Pokemon. And water Pokemon, for example, are stronger against fire Pokemon because water snuffs out fires, right? So it's like a big 15-dimensional rock, paper, scissors game with each type being more or less effective according to this chart. So what I did is one evening out of boredom, I developed a Monte Carlo code to randomly sample the Pokemon types because I wanted to see statistically what was the best Pokemon type, right? Some are strong versus some types and weak versus a lot of types. Is it better to be strong versus a really common type or strong versus several more less common types? So I developed a Monte Carlo code to sample these types to see which one was stronger. It found that steel was the strongest type. Steel, also a good Shaq movie, but also the strongest Pokemon type. It was followed by psychic and normal types. For everyone who's ever played Pokemon, you know that bug types are just the worst type. And as expected, this Monte Carlo method showed that they were the worst type. So Monte Carlo has lots of useful applications ranging from computing pi to predicting Pokemon types. Another fun example, which in this case, fun was kind of in quotation marks, was this past year, about a little more than a year ago. Yeah, a year and like 15 months ago when COVID was really ramping up. I wanted to try and predict how significant the U.S. infection rate would be for COVID. So if you look at the distribution of pandemics, of these kinds of outbreaks, they tend to follow normal or log normal distributions. So what I did is I wrote a Monte Carlo code to randomly sample, like the mean of this distribution, the standard deviation of this distribution, the skewedness of this distribution, all sorts of things to try and develop a model to predict when the COVID rates would peak in the States. It actually was accurate for the first peak that we had. It predicted it within about a day or so. So it worked out pretty well. Of course, the method ultimately did not work in the long term because, well, why? Because the outbreak was a multimodal outbreak, right? You had lots of different peaks. You had all this predictable behavior. People started getting vaccinated. People started ignoring the vaccines. People wore masks. People ignored the masks. All sorts of complicated factors, right? If Ringo Starr said to wear masks and people are going to wear more masks that week, that's a specific event. So there's lots of different factors. It's hard to capture them all, but this model actually did capture them accurately for the very, very first peak of the COVID outbreak. So I thought that was pretty neat. But getting back to nuclear things, which also have some neat Monte Carlo applications, it's worth reviewing the difference between deterministic and Monte Carlo methods. So for deterministic methods, like the SN method or the method of characteristics, we discretize the Boltzmann transport equation in terms of space, energy, and direction. Right? It's basically a 6-dimensional discretization that we do. Once this is discretized, basically it makes a series of matrices which we can solve with rapid convergence. There are often so many matrices that it's hard to solve them quickly, but they tend to solve pretty quickly with a high order of convergence. So deterministic methods give you an exact solution to an approximate version of the problem. It's approximate because the problem has been discretized. Monte Carlo methods are kind of the opposite. You can use the exact representation of the geometry, of the nuclear data, of the angular distributions, right? Particles can have any energy. It's not just several discrete energy values. It's a continuous distribution of energies. However, the downside for Monte Carlo methods and the limitations that the second half of this talk will cover are the statistical side. It's a statistical method because you randomly simulate several particles. If you don't simulate enough particles, your result is going to have statistical noise and it may not be accurate. There are also questions about how many particles do you need to simulate to make it be accurate. So there's all sorts of interesting questions, there are ways to mess up a Monte Carlo calculation by getting bad statistics. And sometimes it's not apparent that you have bad statistics. So with some best practices that I'll talk about in a few minutes, you can the goal of the rest of this talk is to give you kind of an intuition or an understanding of, am I doing the right thing with my Monte Carlo simulations? Am I converge? Will these Monte Carlo simulations have accurate results? If you get the statistics right, then Monte Carlo can be very, very accurate. It can be the golden standard. So, okay. So the goal of the rest of this talk is to understand how we can guarantee that our Monte Carlo simulation arrives at the correct answer. We're also trying to know what hidden traps there are that we need to avoid and understand what best practices that we should follow. So there's, I guess I have this meme of the lab dog who has no idea what they're doing. Our goal for this presentation is to be less like the lab dog who doesn't know what they're doing and more like another more Monte Carlo fluent golden retriever. Let's say Airbud. I think Airbud was probably a lot better with Monte Carlo methods than the uninformed lab dog. So we're going to be less like lab dog, more like Airbud. I know what you're thinking, which is probably, hey Chris, the last Airbud movie came out 15 years ago. I don't know the reference that you're making, and I'm just going to smooth right over this and go on to the next slide. So what are the areas of, what are the traps that we can fall into for Monte Carlo? How can we avoid them? The traps that we have are fission source convergence, undersampling biases, if I can say it, statistical uncertainty, statistical significance, random number generation, and nuclear data uncertainty. So for the rest of this presentation or seminar or lecture or whatever you want to call it, I will go through each of these 6 points and address their impact on Monte Carlo simulations and how you, as a Monte Carlo user or developer, can run simulations to avoid any of these pitfalls. The first of which is fission source convergence. So some of you might be doing fixed source Monte Carlo simulation, in which case you don't need to worry about this. But if you're doing eigenvalue simulations, power iteration simulations, then you're trying to compute the K-effective, the criticality of different systems. When Monte Carlo codes do this, they use different generations of neutrons, where the fission sites that one generation makes serve as the birth sites for neutrons in the next generation. This is done because we don't know a priori what the distribution of fission neutrons should be for the system. So we start with a guess, and if we wait long enough, then that fission distribution will converge towards the true distribution of fission sites in the system. The trick here is knowing that our fission distribution has converged. So the question is, how can we tell that it's converged? And how long do we have to wait until it is converged? These initial skipped generations are the generations that we wait while the fission source is converging. They're called inactive because you're not getting the real answer that way. You're not taking any tallies. You kind of haven't activated the code because the fission distribution is not correct yet. If you take tallies with an incorrect fission distribution, you risk having incorrect tallies. So we want to make sure that the fission distribution is correct so that our tallies are then correct. So let's see. So how can we know that our fission distribution is converged? Well, here's a case. This case demonstrates the problem of a non-converged fission distribution. This example is a OECD NEA benchmark model. Basically, the OECD NEA is an international collaboration of nuclear engineers who come together every year in Paris, France, and work on all sorts of different important problems with the experts in the field in nuclear engineering. I've been a part of these meetings. It takes a great deal of personal sacrifice to meet voluntarily in Paris every April and September. It's just absolutely terrible going there and having all this delicious food and all this delicious wine and seeing the sites and doing all this stuff and working on some really, really awesome science. It's a matter of self-sacrifice that I gladly do for the nuclear engineering community. But one of the problems that this group has worked on is the checkerboard storage of assemblies. So in this case, the dark squares are fuel assemblies, the white squares are water. We have this big spent fuel tank where we have this checkerboard distribution of fuel assemblies. This problem is difficult because it's very, very decoupled. A neutron over here on the right side has a very low probability of interacting with a uranium isotope on the left side of this model. They really only communicate about basically, where's my mouse? To the assemblies right next to them and that not much farther. So if you plot the fission distribution for this model, it looks something like this. So initially, all of the fission sites started in this lower left fuel assembly. If you skip only one generation, then you kind of get the assemblies near it. We got lucky and got some over here too, but not any farther than that. This entire chunk of the spent fuel tank is unsampled. It's just neutrons don't go there. They just don't make it there. With 50 generations, we get a few more. 250, we get quite a few more. And even after 1,000, we still don't get this entire tank. This is just a very, very difficult problem for converging the fission source. It's just neutrons don't communicate from one side to the other. This is important in criticality safety, for example, because what if, for example, over here, we had one assembly that was like the wrong enrichment and that was supercritical or something. So in that case, you might have a supercritical system and not know it. So you might say, this is absolutely safe. Or maybe you have like a super dense reflector on the right side or something, and it makes these assemblies over here supercritical. Maybe they're the same as all the other assemblies, but the reflector is different over here, and it makes it supercritical. Well, when you went and designed the system and actually built it, you would have a criticality safety accident, and someone could get a lethal dose. This is a very serious thing. Lives depend on us getting these simulations right. So the question is, how do we know if our fission source is converged? So here's an example problem, and this kind of shows some steps that you can go through to understand if the fission source is converged. This is actually a model of a criticality safety accident. The accident took place at, I believe at Oak Ridge, actually, either Oak Ridge or Y12 in the 50s. I should have memorized the name of this accident, shouldn't I? But what happened is they had a drum that contained some, I believe, uranyl nitrate solution that accidentally had a higher concentration of uranium than they had predicted. So that caused it to go supercritical, caused a criticality safety accident. Fortunately, no one was really injured or no one died in this accident. This guy right here, this is a recreation of the accident. He saw that it was bubbling over because of the energy released from the supercritical excursion, and he backed away from the barrel right before the criticality safety alarms went off. Him backing away saved his life. There were several other people here who had to evacuate the facility because of this. They actually had their evacuation path was kind of like through here. So it kind of took them closer to the barrel. So paradoxically, by evacuating, they got a higher dose. Still not a lethal dose, but it was a higher dose than they needed to. So this case study is effective for figuring out evacuation plans that maximize safety in case of criticality safety accidents. Anyway, long tangent, but this problem is a good example for looking at fission source convergence, because we have a small volume of high concentration uranyl nitrate, and we have all these other tanks and pipes and stuff around here, which are the red ones in this drawing, that have a low concentration of uranyl nitrate solution. So when you start a Monte Carlo simulation, the default is usually to have a uniform distribution of neutrons. So because it's uniform, that means that most neutrons will be born in these pipes. You have to initialize the neutron distribution, because in a eigenvalue calculation, each generation makes a fission source for the next one. So for the first generation, you don't have a fission source because it's the first one. So you have to start with a guess. And this guess, based on just how it samples the geometry, will put a lot more neutrons in these pipes than in this small little drum. So here we have some parameters to play with: the number of skipped generations, NSK, the number of total generations, Gen, and the number of histories per generation. And we'll look at how changing these values affects our fission source convergence and how it can lead to hidden biases in our results. here's the spoiler alert, but so the reference result for this configuration is around 0.86. The eigenvalue for the drum alone is also about 0.86. The eigenvalue for the pipes is about 0.80. So what we'll see is that some simulations will have a non-converged fission source. It'll have an eigenvalue around 0.80, and as it converges, it'll get closer to this 0.86 value. So how do we know if it's converged? Oops. So here in this case, we have 10,000 particles per generation, 10 active generations, and 3 skipped generations. So here, if you just naively look at this, it looks like the eigenvalue is converged. So what do you want to see from a converged eigenvalue? You want it to be flat, basically. There will be some oscillations, some statistical noise, but you basically want it to converge and flatten out at some value. Here, it looks like it starts flat and stays flat. So it kind of looks like it's converged. However, if you look at the eigenvalue it's converged to, it is 0.80, the wrong one. So in this case, it looks converged, but it's actually wrong. So this is an instance of where best practices can save our butts. So using 10 generations is way too few. You typically want to use for some small, for small systems like Godiva or for like bare, highly enriched spheres, 50 skip generations is pretty good. For a full core, for a reactor, or for some more complicated models, you need to use at least 200 skip generations. This is the kind of best practice minimum number. So 200 skip generations. Looking at this, you should, through the psychic powers that I'm telling you about, you should know 10 or 13 generations, or even 3, are way too few to have a converged result. This is one where you get in trouble because it looks converged and it's wrong. Let's see. This one, here we have half as many particles per generation and twice as many generations. So this is interesting because each simulation is using the same total number of particles, but they get different results based on how we batch them, how we bin them. So here, it's still converging to the wrong result, but there's a sign, there's an indication that it's the wrong result. And that's this little trend that we see, this upwards trend, right? Here at the end, it seems like it's kind of still going, my camera might be reversed, so it seems like it's still going up at the end there. Whereas what we want to see is some fluctuation and then just dead level at the end there. So this trend is what we want to look out for. If you run a Monte Carlo simulation and you see a trend, an upward or downwards trend, that's a sign the fission source is not converged. Here's the same thing again, actually. You see, we see an upward trend, which is great, but the upward trend kind of continues, and it's different from the average eigenvalue. You see that it's like 0.8485 up here and still going up, still approaching the correct eigenvalue. But because there's that trend, that continual upwards trend, we should know that this is getting us the wrong solution. Here, things are good. Here we have some oscillation. It goes up, it goes down, it kind of levels out at an eigenvalue of just above 0.86, which is the correct solution. So this behavior indicates that our eigenvalue is converged. So that's what we want to see. Here it is with even more particles, so you can see the kind of higher fidelity behavior of what we want to see. So another way of predicting fission source convergence, this is a very good way. It's called Shannon entropy. It's a concept from information theory developed by Claude Shannon during World War II. And basically it looks at how much information is contained in messages. Does one message have a lot of information, or is it spread out amongst several other messages? So some fellows named Forrest Brown and Taro Ueki from Los Alamos developed this method. Forrest is like recognized as the god of Monte Carlo. He actually just retired from Los Alamos, but shameless plug, he's giving lectures still at UNM. So we're really happy to have him teaching our students. but they developed this method that uses Shannon entropy that computes Shannon entropy for the distribution of fission neutrons. Basically, you look at the probability that a cell contains a fission neutron or a fission birth site. And long story short, without going into the details, this Shannon entropy is much better at predicting fission source convergence than looking at the eigenvalue. What they saw is that there are some cases, so here, down here is the eigenvalue plotted, up here are H's, which are the Shannon entropies. What happens is that the eigenvalue converges a lot faster than the Shannon entropy. So even analyses like this can be misleading. Looking at the Shannon entropy is the much better metric for diagnosing that something is converged. You know, a way that I think about it is, say you have a symmetric reactor core, right? If all of your neutrons are only in 1/2 of the core, then your eigenvalue is going to be converged because it's symmetric. But your fission source is not converged because it's only in 1/2 of the core. So if you have this big reactor core and you're taking tallies on this other side of it and all the fission neutrons are on this side, you're not going to get any tallies. You're going to think that the dose rate or the fission rate or the flux is a lot lower than it actually is because you're not getting those tallies for a while. So Shannon entropy looks at that, and it looks at the evolution of that fission neutron distribution, and it's a much better metric for determining if things are converged. Here's a plot of Shannon entropy from a scale calculation I did. I used to work at Oak Ridge, so I used to use scale a lot. But you can see very clearly, you know, right around here and right around here is when these simulations are converged. If your fission source is not converged, the main way to converge it is to use more skipped generations. Using more particles per generation has a secondary effect. It has a weaker effect on fission source convergence. The main thing to do is to change the number of skip generations and use more skip generations. Take a water break here. All right, I'll also look at the chat real quick. Cool, no questions so far. Everything, oh. Why do we skip neutron generations? It's for the fission source, so that the fission source can converge. We start out with a guess for the neutron fission distribution. Yeah, yep. Thank you, Raymond. We start with a guess for the fission source distribution, and each generation makes the fission birth sites for the next generation. So we have to start out with a guess because it's the first one, and then we wait until that distribution converges to the true distribution. So we have to skip generations while it's converging, because otherwise those tallies will be incorrect. All right. Yeah, good conversation in the chat. All right. Here's a summary of best practices. I've kind of already gone over most of these. Yeah, I've pretty much gone over all of these. I will say that it's good to do some scoping calculations if you're doing some extensive runs, if you're doing some like depletion simulations or some runs on a big supercomputer or something. Do some scoping runs to figure out what you need to do to converge your fission source before you like launch that job off to the cluster for a couple of weeks. It's a little bit easier that way. You save yourself some worry in the long term. Also, having a good starting guess for the fission source dramatically helps. That checkerboard problem, there we were starting everything in just one assembly. Had you started it in all of the assemblies, things would have converged a lot faster. Okay, next topic is undersampling biases. I'm about halfway through with the time, but each one of these slides will, these topics will go a little bit faster and faster. Undersampling biases. So in eigenvalue simulations, in particular, you can have flux tallies and you can have Monte Carlo tallies for fluxes or fission rates or whatever that have a bias due to undersampling. Basically, undersampling is you don't adequately sample all regions of phase space in that problem, and so it creates a bias, an error that exists that you don't know about. These errors are well outside of the range of these statistical uncertainties. That's also because biases occur in these statistical uncertainties themselves. So it's a difficult thing. Basically, your result is wrong, and the statistics don't indicate that it's wrong. The error bars don't say that it's wrong. And this is just based on it's typically using too few particles per generation that causes these undersampling biases. Again, the biases occur in the tallies and in the tally uncertainties. These biases can be tens of percent, even for some relatively simple problems like just an infinitely reflected fuel pin or an infinitely reflected fuel assembly. The biases will occur in the axial tallies actually in the z direction. So these biases can be pretty nasty for these eigenvalue simulations. There are some metrics that have been developed to diagnose these undersampling tallies. The best practice that we've seen is to use at least 4,000, really more so like 10,000 particles per generation for your eigenvalue simulations. That's the long story short, use at least 10,000 particles per generation. If you're using larger systems, a full core reactor, consider moving up towards 100,000 or more. So that's just a good best practice to have in your pocket. We continue to study this effect. We're still looking at metrics to diagnose it. So this is still kind of a work in progress. I will say that these biases are less common in fixed source problems. That's because you're simulating all the particles at once. You don't have them in batches, and it's a lot of these biases are caused from the batching of neutrons, where it's only 10,000 particles per generation is not enough to represent the fission source for that one generation. That's a lot of the cause of these biases. Fixed source problems, they don't have fission sources, so they don't need to worry about this. So this bias is a lot less severe for fixed source problems. You can have underestimates uh, of some standard deviations in your statistical parameters for fixed source problems, but it's a lot less common. This is more so an eigenvalue simulation thing. Oop, I got bonked. All right, next is statistical uncertainty. Long story short here is use the Wikipedia page. So Monte Carlo tallies are reported with a standard deviation, which is estimated using the central limit theorem and some cool Monte Carlo math that Sean probably talked about this week. But there's this 1 over root n rule that we have in Monte Carlo tallies, which is that if you increase n, which is your simulation runtime or your number of particles, by some factor, then the error decreases by the square root of that factor. So if you use 4 times as many particles, you'll get half as much uncertainty in your standard deviations. So this is useful when you run Monte Carlo calculations because you might have a target. You might say, I want a 10 PCM uncertainty in my eigenvalue or something like that. So then if your simulation has a 100 PCM uncertainty, that means you want to reduce it by a factor of 10. So you have to use 10 squared as many particles. So 100 times as many particles in that simulation to get to your target uncertainty. So what I tend to do when I run Monte Carlo simulations is I'll do a relatively shorter job, not too short, still long enough to get some decent statistics. And then I look at the standard deviations that I have. Typically, get them below a couple percent or something. Below 10%, below 5% is good, even better. But what I do is I run the scoping problem, the initial one, and then I use this square root law to say, okay, this is my initial uncertainty using, let's just say, 1 million particles. If I want to get it down to if I want to get it 10 times smaller or 20 times smaller, then I need to use 100 times, 400 times, whatever, as many particles. So I use this to scope how long the simulation should take and how many particles I need to run to get to my target uncertainty. So you might, as you guys graduate and go out into the workforce, you might have target uncertainties for your calculation. There might be a best practice or something. This rule will help you get there. And this rule applies both to eigenvalue simulations and fixed source simulations. So it applies equally to both of them. So it's a good rule to keep in mind. For statistical significance, this one is, sorry, I mixed up the two. This one is the go read the Wikipedia page. Monte Carlo simulations have statistical uncertainty associated with each of their tallies. So whenever you combine the tallies in some form, you need to propagate this uncertainty and figure out how much uncertainty is in the final thing. So if you add two quantities together, you have to compute their effective standard deviation like this. If you multiply them together, there's a different formula, which Wikipedia has, that you need to compute for the effective standard deviation of that other thing. So propagate your uncertainties is the point of this slide. The Wikipedia page is awesome. It will tell you how to propagate the uncertainties. Taking classes on statistics, also a good approach. Wikipedia is slightly faster, but slightly less thorough. We'll also say that, let's see. I don't quite understand. There's a question in chat. Yeah, so the final uncertainty is reported by MCMP. That's just for the specific tally quantities. So you compute an eigenvalue, for example. If you want to look at the difference between an experimental eigenvalue and the MCMP eigenvalue, you need to propagate the uncertainty this way. So this is for propagating the uncertainty between different simulation results. MCMP handles all the stuff behind the scenes during the simulation, but this is for the individual results. These uncertainties, so they should roughly obey the laws of statistics. Again, these uncertainties are statistical estimates, so they're not exact. But what you can do is you can do like chi-square tests, for example, to compare collections of data and see if they vary if there's a statistically significant difference between them. In general, if you're comparing one quantity, it's good to go for a less than 2 standard deviation difference. That's really the goal. There's about 95% probability that if the two things are equivalent, they'll have less than 2 sigma difference. So 2 sigma difference is the general rule of thumb. In practice, I look at this stuff all the time. If it's 1 or 2 sigma, that means that the quantities are fine. They're agreeing. What happens is if something is actually, if you're getting the wrong answer, if something is disagreeing, it'll typically be like a 5, 10, or like 1,000 sigma difference. So there's a question mark on, is it statistically significantly different if it's a 2, 3, 4 sigma difference? But beyond that, if it's like 5 or 10, then it's definitely different. If it's less than 2, less than 1, that's good evidence that it's the same. And again, if you have collections of things, if you have multiple tallies to compare at the same time, look into doing a chi-square test. That is a good approach for comparing lots of these things simultaneously. All right, next is the random number generator. So the random number generator is used to generate the random numbers. They're actually generated using an algorithm, they're not truly random numbers. You could like sample some system number or something. There are ways to get true random numbers, but we don't want that. We want to have an algorithm. Why do we want an algorithm? Because then it's repeatable. If I write a Monte Carlo code and send it to Y12 for criticality safety analysis, and they see some sort of bug in the 1000th generation, I want to be able to repeat that same exact calculation and get to that 1000th generation so that I can figure out what's going on there. I want to be able to try and rebug it. It's known as making the results of the Monte Carlo code reproducible. So that's why we have pseudo-random numbers. So how random are the pseudo-random numbers? Are they random enough? The answer for that is yes. They are very, very random. So Kino, for example, uses the Mersenne twistor random number generator. And basically, you can generate this many random numbers until it starts repeating itself. That's about 10 to the 6,000th, I think, random numbers. So that's quite a few random numbers. So for all intents and purposes, you're never going to use 10 to the 6,000th random numbers in a simulation. random numbers should be completely random because of this. You also don't really need the random numbers to be super random, just because, like, say for example, you are sampling things on a line, right? A one-dimensional line. You pick the points randomly, and sometimes if they start repeating, then you'll get that same distribution of numbers. However, if you're looking at a 2D thing, right, you're randomly sampling X and Y on the 2D chart, it's much harder to get things to start repeating because you have multiple things you're sampling at the same time. The Monte Carlo simulations we do are like 6-dimensional simulations, right? You have space, X, Y, Z, energy, E, and direction. So mu and phi, right? So you have 6 dimensions. The odds of, your random number seed restarting at the same exact point for the same exact particle when all 6 dimensions line up perfectly is basically 0. So there's basically no chance that your simulation's random number stuff could start repeating itself, just because even if you get to the end of this and it starts repeating, you're going to be looking at a different particle in a different area, sampling a random number for a different thing. So it's no risk of the random number generator being bad. I privately wonder how bad you can make the random number generator and still get correct results. I haven't looked into that yet. I probably should. That'd be a fun little study. These are good ideas. Okay. Next point is nuclear data uncertainty. This is the hidden gotcha in Monte Carlo simulations. So why do we care about nuclear data uncertainty? Well, that's because the input data that we put into the Monte Carlo code, right? When we run MCMP, for example, it assumes that the nuclear data and the number densities and the material densities and the dimensions, it assumes that all of those are exactly correct, and it gives you the result for that one system. But in truth, there are uncertainty in the nuclear data, and the dimensions, and all these things, and it introduces uncertainty in the output quantities and the things that we want to study. So there's a significant degree of uncertainty in these things, which can make a significant degree of uncertainty in the outputs. A lot of my research deals with computing sensitivity coefficients, which is a fancy name for relative derivatives, which can allow you to propagate these uncertainties from the input into the output. So because of these uncertainties, because of the fact that all nuclear data is determined experimentally, and therefore contains some experimental uncertainty, there is uncertainty in the Monte Carlo simulation results. In general, rules of thumb. For fast reactors, there's about a 1% uncertainty in the eigenvalue due to nuclear data uncertainty. For thermal reactors, it's about 0.5%. Why are they different? It's actually because the inelastic scattering cross-sections, which are, again, at higher energies at the fast energy regime, those have a lot more uncertainty than thermal cross-sections. So the inelastic scatter makes these numbers different. Capture is also a little bit more uncertain at those energies, but there's a connection between those uncertainties too. So long story short, you can use these sensitivity coefficients to propagate the impact of these uncertainties and to understand the impact of these uncertainties on whatever you're simulating. Sensitivities are, the way to propagate these uncertainties is known as the sandwich equation. So it's just combining the sensitivity coefficients. If you look at the units, it makes more sense. You combine the sensitivity coefficients with covariance data, which is a fancy name for the cross-section uncertainties. It's called covariance data because the cross-section uncertainties are correlated. So there's a correlation between the elastic scattering and inelastic scattering cross-sections, because neutron comes in, neutron goes out, you don't exactly know if it elastically scattered or inelastically scattered. So there's some correlation in their uncertainty. So you can combine sensitivities with this covariance data and figure out how much uncertainty we have in the thing that we're tallying, the eigenvalue or a reaction rate or a flux or a detector response. Sensitivities are nice. I computed these using the continuous energy tsunami code. They're nice because you can really see these are the sensitivities for some cross sections on the eigenvalue of some system. Here are hydrogen sensitivities. These are U-238 sensitivities down here. And you can actually see how these are like this is a 6.670 V resonance in U-238. It's just a just above thermal capture resonance that actually absorbs a lot of neutrons. It's the main reason that neutrons don't resonance escape. But you can see that the eigenvalue is very sensitive to the hydrogen scattering cross sections at this energy, or very sensitive to the 238 capture cross sections, because increasing the hydrogen cross section allows neutrons to downscatter and escape this resonance. So I like to geek out about sensitivities because you can look at them and understand the physics of the system. Like here's an energy self-shielding depression right here, a dip in the sensitivity right there. Here's a peak in the hydrogen sensitivity because it leads to better resonance escape. So sensitivities can tell you a lot about the physics of the system, and they can allow you to propagate the uncertainty in the cross sections. We are working on getting sensitivity coefficients for more things all the time. I have a student who's, I know several people in the consortium are looking at sensitivities for fission multiplicities in systems like that. There are ways of computing sensitivities for detector responses, reaction rates, obviously eigenvalues. So there's all sorts of ways of getting these sensitivities, and there are more and more every day, or maybe every year and rather than every day. So this is a cool area. Just want to let you guys know about it so you know that you can propagate these sensitivity, the sources of uncertainty here. You can capture the effect of how nuclear data affects your response, how it introduces uncertainty into whatever you're calculating. So that is, oh, I see a question. Let's see. Yes, okay, good question. So there's one question. Is there a tally for the sensitivity in MCMP, or does it have to be found manually? I believe it's the KSEN card, one word, which activates the MCMP sensitivity tallies. So Brian Kudrowski, who's a professor at Michigan, put that capability into MCMP. He has a lot of papers on it. I definitely recommend that you go research them if you want to learn more about that capability. The way to activate it, I believe, is the KSEN card in MCMP. So that is a good thing to look into. All right, so we have come a long way. We are no longer lab dog. We are now airbud. We know how to get our Monte Carlo tallies reliably correct, right? We know the hidden traps, the tricks, the pitfalls, and we know the best practices to circumvent them. So with that, I will bonk one last time, and then I'll conclude my presentation. So thank you all for listening. I know I'm the last one before the break, so I definitely appreciate your attention. Please feel free to ask me questions now, or to contact me at this email address. You can Google me and find me from the UNM website too. And I'm glad that you guys are in the MTV Summer School. Hope you've been enjoying it, and happy to answer any questions.
Great, Chris. Thanks for the great presentation. And thanks to everyone who asked questions during the talk. We do have some time now. If there's any final questions, we can address them. I'm going to ask one. I see some activity here in the chat, but I'm always interested about this. You called it best practices for the number of inactive site goals and all of these things. How are those numbers kind of arrived at, and how firm are they? I know it depends on the application, but can you talk more about those best practices, values, and kind of where they come from?
Yeah, absolutely. So there's a figure in my talk that that is one of the figures used to determine these things. So here we have this is a figure from a publication that I made as part of this working group, the OECD one, that looks into this undersampling effect. But basically here we use the same number of total particles after the fission source was converged, but the same number of particles. So I think it was 100 million in each run. So here we had 1 million particles per generation for 100 generations. Here we had 100 particles per generation for 1 million generations. And here are the tallies that we got. So you could see right here that there's this clear kind of, this is the normalized flux. So basically there's a reference solution that I normalized it to. So you can see that this is like a 10% deficiency. So based on this, this is the evidence that we use to determine, hey, 4,000 particles per generation, which was about right around here, is the minimum. 10,000 is kind of accepted as the norm, which is right here, a little bit past the hump. So these kinds of studies are necessary for doing that.
Mhm.
Mhm.
Is there a reason you looked at pin flux and not, the eigenvalue or some other quantity? I guess because you want the fission source convergence.
Yeah, we so I used the pin flux because it was a little bit more of a dramatic effect. There actually also was an error in the eigenvalue too. It was a little bit less dramatic, so I used this plot instead. Uh, but yeah, there's also an effect in the eigenvalue. The fission convergence is a spatial effect more so, so it tends to affect localized tallies like a pin flux more than a system-wide tally, the eigenvalue. So that's why the effect is greater. You also run the risk of having an eigenvalue that's correct and a pin flux that's incorrect. So
Mhm.
it's the kind of the concept with Shannon entropy too. Like you can't just look at if the eigenvalue is converged. You have to look at if these local tallies or these local quantities are converged.
Right. Great. Last question that I'm going to ask is about, you mentioned nuclear data and you mentioned that the challenges moving toward fast reactors and how there's kind of different uncertainties there. Can you talk more about the directions of research, like which data do we need to look at more closely to help these calculations for next generation reactors?
Yeah, that's a great question. Uh, there are groups that are they're working on that. There's the Nuclear Data Interagency Working Group, basically the NNSA, so the sponsor of the consortium, DOE NE, DOE Isotope Production. So there's like these 5 agencies that make the Fellowship of Nuclear Data or something. There's just like Lord of the Rings. They're on a great grand journey together, but they're looking at the needs of each of the agencies, and they're looking at, are there overlapping needs? Does everyone need something different, in which case you kind of make piecemeal improvements, or is there one underlying thing that affects everyone? So for each of the agencies, they each have their own needs. I know that for NSA applications, fission yields, some branching data, those are like even like beta effectives, actually, the things that you use in the point kinetics equation in your graduate kinetics class or your undergrad reactor physics class, those are actually highly uncertain. So there are lots of ways to improve that uncertainty. For DOE NE, for reactors, it tends to depend more on the reactor design. For molten salt reactors, they've undergone improving the fluorine cross sections, uh, just because those, I think the scattering kernels for them were highly uncertain. They've looked at improving the graphite S alpha beta scattering cross sections. So if you have triso fuel or like a HTGR with lots of graphite reflector, there's an issue there with those scattering cross sections. For fast reactors, this is discovered from the TerraPower fast reactor design. They used, was it NDEF7 versus NDEF7.1, and saw like a 4% change in the eigenvalue of the system, which is enormous. And that's
Huge.
it. Yeah, it's and it was actually because there's a paper that I didn't publish that one. I should have, but it's part of another paper where Reardon is the guy. He's my old boss from Oak Ridge. You can look him up. His name was in this presentation. Um, where we looked at some, we found out by running some sensitivity methods, we found out that chlorine, I think it was a chlorine 35 N alpha cross section was like changed by several orders of magnitude, or I think it like was not just, it was cut off in the old data library or something. So it was just truncated. Cross section was nowhere near where it needed to be. And they changed that they updated that in the next library, and it caused a huge change in the eigenvalue for that system. So it's really interesting. It's really kind of a case dependent thing, which nuclear data improvements are necessary. So it's hard to kind of marry that stuff together.
Yeah.
Personally, I try to move my research in the direction of getting the methods to do that stuff, so that if you're making a fast reactor or a thermal reactor or a pebble bed or whatever, you can use the same kinds of methods to make sure that data is right and to calibrate it if you need to and to update it.
Yeah, great. So we're almost at time, but there is one question in the chat, so we'll take this as our final question. And they're asking about the max number of particles that can be simulated for a typical computer. So can you talk a little bit about how the method scales on different computing platforms?
Yeah. Okay. Yeah, that's an interesting question. So in general, Monte Carlo codes will in general, they do one particle at a time. So in some ways, there's no limit to the number of particles that you can do. Some Monte Carlo codes make there can be memory leaks. There could be other pieces of data that you tally for each particle that will gradually grow the memory footprint of the thing. And eventually you run out of RAM and then you can't do that simulation. I don't know how to calculate that other than like by plotting the RAM usage versus time and comparing that to what particle are you on particle a million, a billion, or whatever, and extrapolating that to when your system runs out of memory. There are let's see, you could run into issues if you're using if you're doing parallel calculations. So if you're doing domain replicated, when you do a Monte Carlo calculation in parallel, you can either do domain replicated, which means you copy the problem several times on each like node or on each processor or something like that, and then each one of them individually does particles. Or you can have domain decomposed, where you have like this one will have half of the core, this will have the other half, and they shoot particles back and forth. They communicate them back and forth between the nodes when the particles cross from one half to the other half. So if you're running it in domain replicated form, where you have the same copy of the problem multiple times, you can run out of memory if you have too many copies of that problem. This is a problem for GPUs in particular, because the whole idea with GPUs is that they're flop intensive. They do lots of calculations, lots of operations very easily, very quickly, but they have a very small cache, basically very small memory. So it's hard to have lots of domain replicated things on GPUs. Actually, the nuclear data is one of the worst parts of it, because it's 1 to 3 gigabytes usually of memory. So if you have 20 GPUs and 3 gigabytes of memory, all of a sudden you have 60 gigabytes of memory and you run the risk of running out of memory. So let's see. I don't know that much about hardware, so I will. There's another question about, does a Tesla V100 or RTX card which one would be more appropriate? I don't know. In general, what do you want for Monte Carlo simulations? In general, you want enough memory. There's ongoing research on making these methods GPU appropriate. So they're getting there. They're not quite there just yet. So in general, GPUs don't gain you much with Monte Carlo just quite right now. If it's an accelerator built into another non-GPU card, then maybe it does gain you something. But in general, for an ideal piece of hardware for a Monte Carlo simulation, I would say I want to have enough memory for the problem, and then after that, as much processing power, as many flops as possible. So it all depends on the problem too, because if you have a small problem, you don't need a lot of cache, right? The cache is the smallest level of memory on a processor, and it like stores stuff in there that the processor thinks it's going to need later. So if you're taking tallies in a big vector, it'll store the entire vector because it thinks it's going to need to use different parts of it around the same time. So if you can fit everything into cache, then that's great. If you can't fit everything into cache, then it's beneficial to have a processor that has larger cache so you can fit more into it. So it's a complicated problem. There's lots of different factors. It's hard to really say that like one thing is better than the other. It depends on the piece of hardware, depends on the kinds of problems that you're solving. So it's really hard to say.
Great. Well, thanks, Chris, for the great presentation and for answering all of these questions. Thank you to the attendees for all the wonderful questions as well. And with that, we will adjourn this lecture. A reminder, there are no lectures next week. So our next lecture will be on Tuesday, July 13th. So thanks, everyone.
Thanks, guys.